Recording in progress.
So I'm going to be talking or introducing rough paths theory and a one sentence summary of rough paths theory is that paths let you solve differential equations driven by highly irregular signals in a pathwise way. Okay. So by highly irregular, we're going to be measuring that in terms of either key variation or Holder continuity. And pathwise, as opposed to, if you guys have seen any Ito theory before, everything is done on averages or taking limits and probability. All right. So this is like just a one sentence summary of what rough paths theory lets you do. Okay. So in particular, we're interested in differential equations, the form of this form, say the sigma Lipschitz and X is our driving signal. Yeah. So for this, this is the prototypical example of the equation we're trying to solve. And our X is going to be, usually it's going to be understood as a stochastic process. That's the case that's the perspective that I'm taking is as a stochastic process. But with rough path theory, everything is done pathwise. So there's nothing inherently random about rough path theory. So X could be a stochastic process. X could just be some generic signal, right? We're treating everything as paths, not as processes, right? And when we do have processes, it's going to be particular realizations of those processes. Okay.
X only appears once in that equation.
The X is the driving signal. It appears here, but the Y's are going to depend on the X. And in general, you can extend it to, you can include the X's in the coefficients as well. You can include the X's in more complicated ways. This is just like a start.
It only appeared once with the derivative, then why not just call it something else and say, anyway.
Call it, what was that?
Well, just change the name. So that, if something only appears once, it doesn't matter what you call it. So if you called it the derivative of something, why not just call it that thing itself? And anyway, but if the Y depends on X, then okay, then that's significant. So X does appear more than once in this equation.
Implicitly, the Y is going to depend on the X, right? Implicitly. And the coefficients can depend on X if you want to deal with path-dependent SDEs, right?
So Y is a function of X and T.
Yes,
Okay.
that is correct. So, yeah, so actually, that was going to be the thing I was going to talk about next is, how do you actually get a differential equation like this? So it comes down to if we have so let's say Y of t is, as you said, some function of t and a function of X, our driving signal. And let's say we wanted to write down the dynamics of this. So take a derivative of this with respect to t. This is just FT plus FX just by the chain rule. So generally, that's what you're asking is our function y of t is going to depend on our time, and it's also going to depend on x, and we're going to write down the s. So if we take a derivative, we get this. So an SDE basically is, like the inverse problem of this, right? If we have this, we want to find a y that depends on t and the driving signal. Okay. Now, of course, the issue here is the x, right? So highly irregular signals, in particular, means not differentiable, right? That's a very, very important point. So one point I want to make is that the lack of differentiability of x is sort of a feature of stochastic processes, right? It's not like we can choose, like there are stochastic processes that, are differentiable, are smooth, whatever you want. But in general, in order for stochastic processes to satisfy nice properties, they're going to lose nice properties probabilistically. They're going to lose nice properties analytically, okay? So let me just give a few examples of this phenomenon. One really important one, I think as a start would be if X is analytic, X is, not random, other than maybe a random initial condition, right? Analytic means if you know the value now and you know the behavior now, you can tell the entire future of the path. So if we're having a stochastic differential equation, the noises can't be analytic at all. Unless we want a deterministic differential equation, right? So that's one example. Another example would be Markov process. So if X is Markov and say absolutely continuous, then X is not random, or in the same sense, you might have a random initial condition, but and by absolutely continuous, I just mean it has a a weak derivative. So X of t. I just mean say whatever little x of s. Yes. Can't be Markov, right? Because it depends on the entire history. Okay. What was that?
You have anything absolutely right?
Yeah. There should be an x naught. Yeah. I'm just assuming x of 0 zeros. Yeah, ignoring constants, right? But the point here is that, yeah, if you're Markov, you might have a random initial condition. And your x sub 0 might be random, but the evolution after that has to be deterministic, right? So Markov and absolute continuity don't go together. Similarly, if x is a martingale and x has bounded variation, BDG inequality implies that it is basically not random, right? So that's another important one. If X is martingale.
Is that how you prove the statement? That if you are having continuous, if you are not
if I get to saying that it's both those things, then look at the 2 points there, there has to be a constant.
Yeah. So I'm just saying it is this integral. I mean, this isn't a proof. There is a proof out there which require a little bit more. I'm just saying if you look at this, it should be true. Like kind of intuitive that it's not actually Markov.
For running motion, you can see it, but the question, suppose you have a process and you say that I'm not going to restrict my future path to be those for which condition holds.
Mhm.
Can you construct an artificial Markov chain by restricting the sample path and
I don't think so. There's one proof. There's a proof in an some very old classic paper I can send you if you want of this. They proved it for rather than absolute continuity, L1 differentiability or something like that. So I can send you that paper if you want, but it's true. Sure. Again, if X is a martingale, BDG inequality, say X is a martingale with bounded variation, then BDG implies not random. Again, maybe you have a random initial condition, but not random after that. Okay. So the point I'm trying to make of this is just that for stochastic differential equations where we have a signal, most of the signals we care about are not going to satisfy nice analytic properties, right? EDG, I'll talk about it later. It's an inequality basically in terms of the quadratic variation of the supremum of the process. I'll talk about it in a little bit, but basically you can bound the supremum pathwise of a process in terms of the quadratic variation. And if it has bounded variation, then the quadratic variation is 0. So the supremum of it is just going to be 0. It's just going to be whatever the initial condition is. But I'll actually say what BDG inequality is soon. Okay. So the point is, in many cases, dx dt does not exist in many cases, right? So what people do, or the idea is rather than have this be a differential equation, this will be a integral equation. You can translate this to an integral equation. So we're interested in the integral equation. We're interested in this integral equation here. Okay. So this necessitates to define the second one. So the first one, the first integral here, we can just define that as a Riemann integral. It's no problem. The second one here is the problem. All of rough paths theory was created to handle this. That's it. That's all rough paths theory is doing. It's handling that integral. Okay. So a couple of points is if you guys recall from just a standard analysis class on Riemann-Stieltjes integration, we can define that integral as a Riemann-Stieltjes integral if the x is of bounded variation, right? So just want to recall. Well, if G is of bounded variation, continuous, and F is continuous, then exist as a Riemann-Stieltjes integral. Right. So, as I said before, for many cases of X is not a bounded variation, right? Now, one other fact. So I just want to be really precise with, with a statement, the converse of the statement. So if G is not a bounded variation, then there exists some continuous F such that the Riemann sums doesn't converge. So another fact is that if G is not a bounded variation, G is not a bounded variation, then there exists continuous F so that for some partition or some sequence of partitions Pn, so those are going to be partitions. We have that sequence of partitions with the mesh size when it's 0. That guy does not exist. So you're always able to find a continuous function where you're not able to Riemann-Stieltjes integrate against it, right? So the Riemann-Stieltjes integral doesn't help us here. At least classic theory does. I'll talk about Young's theory of integration soon, where this fact here says that there exists a continuous F, right? We don't want to integrate every continuous F in here. We only want to integrate the functions that behave something like this. So I'll talk about the Young integral later, but we can weaken this a little bit. We can weaken these a little bit. Yeah. So we can integrate things that behave like that sigma term, basically in terms of the Holder continuity of it. Okay. So
And one thing you commented, the remarkable aspect of Ito's analysis is that even though the boundary motion is not a boundary variation, the expression makes sense, but in a relaxed sense.
yeah, I was just going to get to the Ito idea is that you weaken it to rather than, so right here, this and that, those are just about functions, not about processes, right? The Ito integral, you look at that Riemann sum, and then you take the convergence, you weaken it from almost surely to improbability, right? So that's what the Ito integral does, is it weakens from pathwise to improbability. And then that actually does exist. The limit improbability exists, the limit almost surely does not. All right, so I was actually just going to get to the Ito philosophy, which is exactly what you had said. So the Ito philosophy is weaken almost sure convergence to pathwise or to limit improbability. Okay, so we weaken from pathwise to limit improbability. All right, so we take a look at the probability limit. And then the main achievement here is that if X is a martingale, or more generally a semi-martingale, this limit exists for, for nice enough F, right? If X is a semi-martingale, this guy here exists. For, say, nice enough F, right? So if we have a martingale or a semi-martingale, and I'll define that in a second, I'll remind you guys what a semi-martingale is in a second, then we can just take the limit in probability. The problem, of course, is if you're doing any kind of application and you have a particular realization of your noise, you're not able to construct an integral from it in general. That's a really big problem here, is that, in any kind of application where you have real data, this limit in probability doesn't quite make sense, right? I mean, Ito theory works, tremendously well. It's been very, a lot of work has been done on it. It's a very rich theory, but that is certainly one of the drawbacks, is you don't have the pathwise convergence.
Anything else in F is continuous?
Say F is continuous in that, or sure, yeah. Basically, really, the process here has to be progressively measurable, and almost surely L2 and all that stuff, right? So that's really what we mean. And it doesn't even have to be exactly of this form. It just has to be progressively measurable, right? So.
There's a worst statement saying that G is not on the variation. The continuous function such that the partition summation goes to infinity.
Yeah.
If you restrict the function F, you don't continue to, let's say, to Lipschitz continuity. Is it wrong?
I believe so. So I'll get into the Young theory of, or actually for Lipschitz continuous, then it is, for Lipschitz continuous, then it actually does converge, as the Young theory will show. But the point is, if your function depends on the path, like if it's a C1 function of the path, then it's not Lipschitz, right? That's a really important point here, is that, if, f of x, so if you have so consider f of x, basically f of x is, generically not Lipschitz, right? All you can say is if f is in C1 with bounded derivative, then f of x of t minus f of x of s is equal to f prime of c, x of t minus x of s. And if you're bounded, so the point here is that if you're a function of the path, then you would expect to have basically the same continuity properties as x of t minus x of s. And if this is not Lipschitz, it's hard to expect this to be Lipschitz as well. So it is true, if your f is Lipschitz, and your signal x is holder for any positive holder, then it does exist almost surely. But that completely precludes anything that depends on the path, right? So, yes. So yeah, let me actually mention a couple other simple cases before I talk more about the Ito theory. So there is this case, but there's a couple other basic definitions that we could make, basic choices. So really the point is, the point here is we want to define 0 to t of f of t, comma x of t, say x of s, b x of s, right? So a couple really basic cases we can make is, if f of s of s is just some constant, well, we can just define this as c, c x of t minus x of o, right? That's just a definition we can make. If f of s, x of s is equal to just f of s if it doesn't depend on the path, and then this is in C1, just a differentiable function of time, we can make the definition plus boundary terms. So we can just make that as a definition. That's a completely acceptable definition, just integrate by parts, right? So if our f just depends on s and is say C1, we can just integrate by parts and make this as a definition. Yes, just ds, right? So really the important thing that we need to deal with is when f really does depend on x, right? That's when it matters. Okay. So as I said, we can do that through Ito theory, right? But one problem with Ito theory is, as I already said, it's not a pathwise theory. The second problem is there's a classic theorem of Bichteller and Delacree that you can only extend Ito to what are called semi-martingales. You cannot go further than that. All right. So let me just remind you of, or tell you what a semi-martingale is. And then so there's a classic Bichteller and Delacree that Ito theory can only be extended to semi-martingales. And what exactly this means so I'll define that in a second, but what exactly this means, I don't want to get too much into all of this theory, but it's very classical that you can only, that semi-martingales are the only good integrators, and we mean that in a precise sense. I don't want to get too deep into that rabbit hole, but let me just remind you. X is a semi-martingale. If x of t is equal to m of t plus a of t, where m is a local martingale. And A is a catalog, so right continuous, left limits, adapted. And locally finite variation. So you can do Ito theory for martingales. You can generalize that slightly to local martingales. That's fine. And then if you have a finite variation, then that just becomes basically a Riemann solution, and it'll. We were still taking limits in probability, but that's basically the idea. And Victeller-Delegris says that you can't go any further than this. Okay. All right. So these are the main two problems of Ito theory. It's not pathwise, and it only handles semi-martingale. And soon I will give you an example of non-semi-martingales as fractional Brownian motion as like the first example. But before that, let me just mention something that Ito theory depends crucially on, and that is the quadratic variation. Okay.
Like for many of us, the first time we are seeing what it is to have a martingale to be the Cadillac function.
Okay,
It's okay.
sure. So,
Yeah, you don't need to define that.
okay, so let me just say local martingale is just, you have a sequence of stopping times that diverges such that the stop process at every stopping time is a martingale. It's basically integrability condition. Catalog just means, right continuous with left limits. And then, finite variation means finite variation. But yeah, so Ito theory relies crucially on what is called the quadratic variation. So let's say, let me define what quadratic variation is for a process. And then I'll say in a little bit what the quadratic variation is not, and that is the two variation. So I'll mention that in a little bit. So definition. So let this be a process, stochastic process. If for all sequences of partitions Pn with the mesh size of Pn going to 0, we have the limit in probability. Exists. So this is these partitions would be on just some interval. So let's say Pn 0 equals T0n and Tn n, which is equal to T. So just a partition of the interval 0 to T. If that exists, then this is called the quadratic variation.
Just to make sure, when you say the limit existing probability, you're saying there is a number 7 such that the probability that the difference between this cell is going to be epsilon
Mhm.
is zero, as n goes to infinity, no matter what epsilon.
That's right. Yeah, that's right. Yep. Existence probability. And also you can even show for processes that if you restrict the class of partitions, that this limit actually converges almost surely as well. So for example, if it's a nested or dyadic or anything like that, it converges almost surely.
Maybe that's a good question. I haven't seen it before, but the set that just goes wrong, like this probability,
Mhm.
like, is that gonna be independent of the partition, like you're saying for all?
No. So what ends up happening is that for almost every path, so I'm just going to stick with Brownian motion, just so, yeah, I'm going to stick with Brownian motion here. For almost every Brownian path, there exists a sequence of partitions so that this limit diverges on that Brownian path for almost every path. Okay. But if you have a sequence of partitions where the, they're either nested or they are, they're either nested or some other conditions like the mesh sizes are summable or sorts of things like that, then you actually get almost sure convergence for that. So the point is the set for which this fails or the sequence of partition for which this fails depends on each path. Okay. That's a really important point, is it depends on each path. I don't want to get too mixed up into that, but there was one book, Renee Schilling, is Brownian Motion Introduction to Stochastic Processes. The chapter 9 in there covers this in full depth. It's like an entire chapter, almost essentially dedicated to the quadratic variation. Okay.
Pick up on Francesco.
Yeah.
Quadratic variation, isn't that a random thing?
Yes.
So I thought Francesco said 7. It must have been a random 7.
Yeah. Well, for Brownian motion, it's going to be
7.
T, but it is a random variable.
Yeah.
But for Brownian motion, it's T, and for a lot of other cases, it's just going to be deterministic. But yeah, you're right. It is the limit is going to be a random variable. That's right.
But when you do this for the Brownian motion, you get T almost surely if you do the next one.
That's right. That's right. You get T almost surely if you do nested partitions or some other things. Yep.
It converges to a non-random.
Yes. Converges to a non-random random variable. Yes.
Yeah. That's what those mean.
Yeah. All right. So let me mention a couple of things about the quadratic variation, and then we'll get into fractional Brownian motion, which is the first example of a non-semi-martingale. Okay. So facts. Is the quadratic variation exists for any martingale. So for any martingale, that limit in probability exists. Okay. And by exists, I just mean, exists, it's finite, everything. And so quadratic variation is, non-trivial for, for any, for any martingale that's not like constant. Okay. So the first one's very classic Ito theory. The second one, let me just mention, this is can be proved by BDG. BDG inequality. It's like Burkholder, Davies, Gundy inequality. So M is a martingale with M of 0 is equal to 0. And m star of t is equal to soup over s less than equal to t of m of s. Then for all p, there exists little cp, big CP, so that the square bracket here is the quadratic variation up to time t. Okay. So BDG inequality says that the, let me restrict P greater than or equal to 2. I think it's 1, but let me just to be safe. Basically, if the quadratic variation was, 0, almost surely, then we get that the process here, the soup over the process is 0, this expectation. So the soup is 0 almost surely, and the process is just trivial, right? So for any non-trivial martingale, you have a non-trivial quadratic variation. The bracket, I said the bracket, this here is the quadratic variation. That's the quadratic variation up to time t. So remember, we're on a partition of the interval 0 to t. And actually, you can even do this. This is generalized to stopping times and things like that. But at least for the point I was making is that quadratic variation is non-trivial. It's not 0 for any non-trivial martingale.
And then for the primary motor solution, is t to the power of q.
Yeah. Mm-hmm. Yep. That's right. So one thing I want to mention is something that the quadratic variation is not, and that is the 2 variation. Okay. It's not a big point, but a lot of people are, a lot of books are not super precise about this, but let me just make this point. It's that is not Q variation. So the P variation of a function f is soup over all partitions of f of tk plus 1 minus f of tk squared. So if you notice here, we're taking a limit in probability over the sequence of partitions where the mesh size is going to 0. The P variation that you know from standard analysis is just going to be the supremum over all partitions. And one really important fact for Brownian motion, so for Brownian motion, the quadratic variation, this bracket here, t is equal to t. However, the 2 variation of B is infinite almost surely. Just one point I want to make here is that for every Brownian path, or almost every Brownian path, you can always find a sequence of partitions so that the variational sum diverges. Okay?
Not thinking about the P variation, should that, the exponent,
That should be a P, yes. Sorry about that.
two P's, a capital P and a little p, right?
Yes, it's
P and a Roman P.
this is script P for partition, and then that is P for exponent.
P variation, there's no like P, there's no like.
This is this is for a function
Might not do it.
on, and these are partitions of your interval 0 to t. That's right. All right. So I've a couple of minutes left. I wanted to get to Brownian motion. If you guys are,
So what kind of P for the drawing motion that variation?
it would be P greater than 2. So for P greater than 2, it has finite P variation. For P exactly equals to 2, it has a finite quadratic variation as its limit in probability. And then it's just infinite other than that. Okay. So I have a couple minutes left. I wanted to mention FBM, but maybe I should wait until tomorrow to introduce FBM. But let me just say a couple things about fractional Brownian motion. It's the first example of a non-semi-martingale. And basically where it comes from is you take a Brownian motion and you just allow a little bit of correlation, or as much as you want, but you can allow some correlation in the increments of the Brownian motion, and you get a fractional Brownian motion. Immediately breaks all the semi-martingale theory. So in this sense, the Ito theory is sort of not robust in the sense that, you know, you introduce a slight epsilon amount of correlation, and I'll be precise with what I mean by that soon, but you introduce an epsilon amount of correlation in the increments, all the Ito theory goes out the window and you can't use it anymore. So the Ito theory is like working right on this kind of like boundary, and you know, Brownian motion sits like right in the middle of the two regimes of the fractional Brownian motion. So it's like this very critical. And the exponent P equals 2 is very critical as well. So.
Exactly. Either is not robust to such a even small perturbation. How would you explain the success of people? In practice, nothing is wrong with it. Where everything is.
Sure. How would I explain it? I mean, it does have a good theory, and in you know, Brownian isn't a bad model in a lot of ways, right? And everything here works. And you know, there are issues with pathwise theory, and I guess like the way I would try to explain the success is, you know, what else is there? I mean, we have the rough paths theory, but you know, that gets pretty technical, and that wasn't developed until a lot later. So Ito theory just has a lot longer. There's a lot of theory that is very important, and it really, I mean, it really is a nice theory, but you know, you know, it's definitely not robust to these little changes, and definitely has some issues. Yes.
When you mention Ito theory, do you include stuff like structural knowledge, integral, some of the things your samples and
So actually Stratinovich, so I have a result. I have a paper in Anala's IHP where if you take the Stratinovich integral of a Gaussian process with that's Holder continuous between 1/4 and 1/2, that converges almost surely to a rough integral. So the Stratinovich is actually very robust. However, there's a few issues with the Stratinovich, is it's sort of anticipating, right? You have to sort of look into the future, right? So that is one of the.
the right hand point, the middle point, the second point.
Yeah, you take the average, right? Yeah. Right. So that's definitely one issue with Stratinovich theory. It does converge almost surely for a very broad class of Gaussian processes, and that's a result that I have. So.
I'd like to answer maybe my own question. When you say adding correlation, probably say correlation in a particular, because you can say that your driving noise is not wrong, it's still marking it. You already have a correlation there, right?
Yeah.
In a sense, you're not supposed to certain correlation, but not all of them.
Right. Yeah. But fractional Brownian motion is just a very slight generalization of Brownian motion. And we'll talk about that soon. But all right. See you guys tomorrow.